This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today I am discussing certain problems, important problems in a thick cylindrical shell in mechanics of solids. In order to derive the equations for the distribution of radial stresses as well as the circumference stresses, we have taken assumptions from the Lemis theory because the problems which are involved in thick cylinders are more complex in nature. The Lemis theory assumptions are: the material is homogeneous, that is isotropic, and obeys the Hooke's law, that is the stresses within the proportional limit now. And second one is the plane section of the cylinder normal to its axis remains plane and normal even under pressure. The longitudinal stress and the longitudinal strains are always remains constant throughout thickness of the cylinder. Since the longitudinal stress is sigma 1, longitudinal strain epsilon 1 are in constant, it follows that the difference in magnitude of hoop stress as well as the radial stress at any point on the cylinder volumes remains constant. Okay, these are the Lemis theory. He made assumptions while deriving an equations. Okay, the stresses in the cylindrical shell now. For determining that certain formulas will be derived. Okay, in this case, we are assuming R1 is representing the radius of the outer cylinder, and R2 is representing the radius of the inner cylinder, and L is representing the length of the cylinder now. Now considering a ring at a distance of x from the center of the spherical shell having the thickness dx as shown in a figure now. Okay, on this ring, let Px is representing the internal, that intensity of pressure is inside of the ring, and the Px plus dPx is representing the intensity of strings on outside of the ring. The ring thickness already we assumed it is equal to dx now. That is sigma x is representing intensity of hoop stress induced in the string now. So based on these assumptions now, what do we made now? Here three types of stresses are acting on the cylinder. One is hoop stress, it is also called circumference stress, having tensile in nature. And the radial stresses, they are acting toward the center, having compressive nature. And longitudinal stress remains constant. Longitudinal stress as well as the longitudinal remains constant. Just the entire thickness of the walls. Just based on these assumptions we made, we determine the pressure, that is radial pressure. The distribution is given by Px is equal to B by x square minus A now. Similarly, sigma x is equal to, we got B by x square plus A now. We derived these equations in a previous section now. These are useful for us, how the radial pressure as well as the stresses, how they are now, intensity of hoop stress, how it is varying just along the thickness of the wall can be determined. The values of A and B, these are the constants, integration constant, and these are evaluated just based on the conditions of the fluid pressure. The above two equations is also called Lemis equations. And when the fluid pressure is acting just inside the cylinder now, three types of stresses are induced in it. One is a radial stress, that is having in compressive nature, hoop stress having tensile, and longitudinal stress, it is the remains constant along the thickness of the wall. The intensity of a pressure outside of the thick cylinder is taken to be 0 here, it is equal to 0. This is nothing but one assumption. Even though there is some hoop stress due to the pressure inside the cylinder, it is active now. Okay, based on this assumptions now, just we are solving certain problems in the cylindrical shell. Here the problem is there, a cast iron pipe of 400 mm internal diameter and 100 mm thickness carries water under pressure of 8 newtons per mm square. Determine the maximum and minimum intensities of hoop stresses across the section. Also set the radial pressure distribution and hoop stress distributions across the sections. Here we are assuming, here R2 is representing the external radius of the cylindrical shell, R1 is representing external, R2 is representing internal radius, T is representing the thickness of the shell. According to the problems, internal radius is equal to R2 is equal to 200 is given. The thickness is given, T is equal to 100 mm. So, external radius is equal to, we can take it as now, internal radius plus thickness, that is which is equal to 200 plus 100 which is equal to 300 mm. The internal pressure is equal to Px is equal to 8 Newton per mm square is given data. Let sigma x is representing the hoop stress at any section and Px is representing radial pressure acting at a section x from the center. When x is equal to 200 mm, that is nothing but it is equal to R2 value. Px value is equal to 8 Newton per mm square. This is the given now. Pressure inside the cylinder now. Similarly, according to the assumptions at outside the wall, the pressure due to the fluid pressure at outside is equal to 0. That is, when x is equal to 300, then Px is equal to 0 now. According to Lami's equations, the pressure at the inner surface is given by, that is Px is equal to, the equation is B by x square minus A now. Just based on this equation, so here at x is equal to, we have taken just inside now, that is the 200 now, that is B by 200 whole square minus of here now, minus of here now. Or from this relation now, B by here 40,000 minus A, or A is equal to B divided by 40,000 minus A now. Okay, this is the equation number 1 we have taken. And again, the pressure at the outer surface now, that is when x is equal to 300, it is given now. Just by using the same equation, Px is equal to B by x square minus A, we got to 0 divided by x is equal to 300 whole square minus A, it is equal to B by 90,000 minus A, or A is equal to B by 90,000 now. Just equating this equation number 1 and 2, we got B by 40,000 minus 8 is equal to B by 90,000 given now. From this equation, so we got here 9B minus 9 into here it is given now 3,20,000 equal to 4B. For these relations now, 5B is equal to, that means 9B minus 4B is equal to 9 into 3,20,000, or B is equal to 9 into 3,20,000 divided by 5, which is equal to, we can take it as 5,76,000 values now. That is B values. So A is equal to B by 90,000 now. From this relationship we got to, here B is equal to 5,76,000 divided by 90,000, which is equal to 6.4. So the hoop stress at the inner surface is equal to, that is x is equal to 200 is given by, that is 200B by x square plus A, which is equal to B is equal to 5,76,000 divided by x square, x is inside is equal to R2, R2 is equal to 200 whole square plus A value is equal to 6.4. From this relationship we got to 20.8 Newton per mm square. Similarly, the hoop stress at the outer surface is equal to, that is R1 is equal to 300 now, Rx is equal to 300, which is equal to B by x square plus A, which is equal to B is equal to, already we have taken, we determine the values, so 5,76,000 divided by x square, that is 300 whole square plus 6.4. From this relation we got to 12.8 now. So now radial pressure Px and rope stress distributions across the sections. Here it can be here now taken as radial pressure. It is having just 8 Newton per meter square at the inner now, and so we are taking now, and it values is 0 at outer surfaces. Since it depends upon the square of the distance now, here we are taking parabolic curve as shown in figure now. Similarly, the hoop stress is equal to, at inside is equal to, we got to 20.8 now, 20.8, and this at outside is equal to 12.8 in downward directions, and these two values nothing but you have to join by using the curve, parabolic curve, because it is depending on square of the distance, so you have to join. This is nothing but representing the how the hoop stress as well as the radial stresses that are varying from this inside the cylinder to outside the cylinder. It is also represented n on xy plane, that hoop stress along the this y axis and radius along the x axis now. Here it is equal to 200, we are taken now 300. Here we are taken. Here pressure is equal to 8. Here pressure is equal to 0. Here it is equal to 20.8, 12.8. These are nothing but how it is changing the values now. Okay, by using this Lewis theorem, we can determine how the stresses are distributing just within the thickness of the cylinder. The second problem now, a thick metallic cylinder shell of 150 mm internal diameter is required to withstand an internal pressure of 8 Newton per mm square. Find the necessary thickness of the shell now. If the permissible tensile stress in the section is 20 Newton per mm square now. Internal diameter of the shell, assume this here given now, dt is equal to 150 mm. But we are calculated the equations based on only the radius. So internal radius is equal to R2 is equal to 75 mm. Px is equal to given now, the fluid pressure 8 Newton per mm square given. Permissible tensile stress sigma x is equal to 20 Newton per mm square. These are the given data now. Here for the solution we are assuming R1 is representing the outer radius of the shell now. From the diameter of the shell, when x is equal to 75 mm, x is equal to 75 mm, that is nothing but R2 is equal to Px values is given 8 Newton per mm square and sigma x is equal to 20 Newton per mm square. These are the values are given now. So from the Lewis equations now we got here 8 is equal to b by x square minus a, which is equal to b by x is equal to 75 whole square minus a, b by 5625 minus a. Or a is equal to b by 5625 minus a. Assume this is the equation number 1 now. And also for the permissible stress sigma x now, here 20 is equal to b by x square plus a, we are given now. Sigma x is equal to here b by x square plus here is given b by 75 whole square plus a, which is equal to b by 5625 plus a, or a is equal to 20 minus b by 5625 now. So equating equation number and 2 now, we got to b by 5625 minus 8 is equal to 20 minus b by 5625 or 2b divided by 5625 equal to 20 plus 8 it is equal to 28, or b is equal to 28 into 5625 divided by 2, or from this equation we got to 78,750. That value is equal to b now. Now substitute the values b in the equation number 1 to get the values of a, which is equal to a is equal to, that is 78,750 divided by 5625 minus 8, which is equal to 6 values now. Now from the Lewis equations of internal pressure, here 0 is equal to, we are having 78,750 by R1 square minus 6 now. Because here internal pressure, that is nothing but at outside of the cylinder is equal to 0 according to the Lewis equations. That is when R1 values, when we are taking, that the pressure is equal to 0. Hence we are taking from this equation Px is equal to here B by x square minus here now. When x is equal to here now R1 B by R1 square minus here now. A is equal to B is equal to already we determined, which is equal to 78,750. R1 value we have to determine. A value is already given, it is equal to 6 now. From this relations R1 is equal to, we got under root of 78,750 divided by 6, which is equal to 114.6 mm. For the design point of view, generally we have to take it as the higher values only, which is equal to 115 mm now. And so the thickness of the shell is equal to, we are having thickness is equal to, here is equal to, it is the difference of outer radius to inner radius, that is R1 minus R2. From this relation, so 115 minus 75, which is equal to 40 mm is required now. Okay, these are the textbooks followed for collecting the above materials now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.